So this is Specimen Paper 1 from the wonderful new AS Chemistry. This is just the AS, so it only takes into account if you look at the specification, obviously the topics are not just A-level as well. Few changes. This obviously is the specimen paper, so it's not a real one. I'm assuming this is what the real one's going to look like, I don't know. Hour and a half, so longer than the AS papers, or longer than the unit 1 of the old AS papers. Usual things, data sheet, blah 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 blah, blah, ruler, calculator, yada yada yada. Maximum amount of paper is 80. This is split into two sections. Section 1, or the first section, section A, whatever they call it, is 65 marks, and is your standard sort of short, medium, long answer questions. Then moving into section 2, where you've got multiple choice, 15 marks of multiple choice, which is, well, certainly while I've been teaching, the first time at A-level we've had multiple choice. Used to do it at GCSE many moons ago, but it's now part of the A-level as well. So I'm hoping hour and a half, hoping to do this in about, I don't know, just over an hour would be good. So the video is not just too long, but there we go. So periodic table deduce the full electron configuration of calcium. This is a standard atomic structure question. I'll try and talk about which topic things are from and give a bit of an idea behind it, but most of this now should be, if you're looking at these papers, you should have a pretty good understanding of what's going on. So we've got our first one. We know from a periodic table that we have 20 electrons in calcium. So what we're basically trying to do here is split those into our correct orbitals and main energy levels and all the rest. So we're going to have 1 S2. So we've used 2. We've filled, obviously, that the first energy level only has 1 orbital. We're going to go then into our second, so 2s2, and we can fill the 2p6. So we've currently used 10, 6, 8, 10 electrons. We've got another 10 to go. So we're going to go 3s2. We'll go 3p6 as well, and we'll end up in the 4s2. We would imagine to have this 2 here, the fourth energy level has 2 electrons, and that equates to it being in group 2 as well, which is quite useful. So this whole sort of first question is really tying into that kind of the inorganic stuff of group 2, but it's pulling in stuff, as you can see now, from, and this would be the physical stuff, which is the atomic structure or electron configuration. So going to ionic equations, reaction of calcium with an excess of water. So calcium and water produces calcium hydroxide and hydrogen, but that's not going to cut it because that's not an ionic equation. So with state symbols, so we start off with calcium, solid, and we're reacting that with water, which is of course a liquid. Don't put aqueous for water because it's not. Splitting off, we produce calcium hydroxide, but this is split into the calcium ions, which of course are dissolved in water, and hydroxide ions, which are again dissolved in water, so aqueous for both of these, and then hydrogen as a gas. Bear in mind here that obviously normally we would have CaOH2, which means you need to equate for that here. So it's the Ca2 plus and the 2OH minus, both of which are aqueous, and we balance this all up by putting a lovely 2 here, which should give us equal amounts. So we've got 4 hydrogens there, 4 hydrogens, 2 oxygens, 2 oxygens, 1 calcium. Yeah, fine. 1 mark. Quite a lot of work for 1 mark, really, but you know, just go with it and do your best. State the role of water in the reaction with calcium. So this is now tying actually into redox, in that we can see calcium here has been oxidized. It's gone from an oxidation state of 0 to 2 plus, or plus 2, whatever you want to say. Water has caused this to be oxidized, therefore water is an oxidizing agent. So pulling in redox now into this part as well, which actually means, you know, it's already got 3 topics now in this first question. Write an equation to show the process that occurs when the first ionization energy of calcium is measured. So this kind of ties into redox here, but it's also that first topic of atomic structure. Calcium becoming calcium plus the first ionization energy. Important that by definition these must be gaseous, and of course we have to have the electron, which is being taken away from calcium, but by convention we write it as being added onto that side. That's going to get you another lovely mark. State and explain the trend in the first ionization of the elements in group 2 from magnesium to barium. So we're going down the group, I believe. I've not got a periodic table on me, so I'm trying to work this out. So we're going down the group here. Okay, as we go down, what's happened to the first ionization? They're going to decrease Well, why is that the case? Okay, as we go down the group, we know that our atoms get bigger. Okay, so as they get bigger, so that's part of our explanation there. I would put atoms here. I would say I've just got the mark scheme here, and it actually says ions. Oh, it says ions get bigger. Really, the first ionization energy is actually taking the electron from the atom, though, so surely it should be atom rather than ion. So I'm going to go atoms get bigger as we go down the group. And what we're talking about there, getting bigger because we add more energy levels on. So we have, obviously, 1 energy level, 2, 3, 4, etc., getting bigger. We do get more protons, but the fact that the atom gets bigger actually cancels that effect. And why I say about protons is that creates a more positivity within the nucleus and therefore a stronger attraction in theory, but because the atom is getting bigger, it's cancelling that out, and actually what we find is that we get a weaker attraction. Now the mark scheme is actually saying here weaker attraction of ion to lost electron, but I'm not. I think that's a terrible answer. That's crap. That's really poor. I would prefer weaker attraction electron being removed, and I would go with that, and that's a much better answer really. That's so far I'm really unimpressed with the specimen paper. So trend anyway. Decreases as we go down. The reason is the atoms get bigger because we get these more energy levels, which essentially means that those outer shell electrons, which are the ones being removed in this first ionization energy, they are less strongly attracted to what is essentially the nucleus, therefore more easily lost. Weaker attraction, easy. 3 marks there, not too bad. Okay, on to question 2. Sorry, you can see they've got this new style of questions as well, where it's just 2.1, 2.2, no A, B, C or whatever, which is fair enough, I guess, but again, not overly impressive. But there we go. Okay, so we've got sulfur consists of 3 isotopes. And table 1 gives a relative abundance of 2 of these isotopes. Right, okay, this is a flip around the question. So we're given the relative atomic mass of 32.16. I'm going to put that here because I'm going to scroll down slightly. We're given the relative abundance of 2 isotopes, and basically we've got to find the mass number of the third. Oh, this is a dark question. Okay, first off, our other isotope here, which is essentially going to be X. I should not have written that there. Where's my rubber? Oh, where is it? Rubber. Okay. So X, and that's going to be something, and we'll put this 32.16 over here. So we've got relative abundance in percentage, which is important because we know that percents must equal 100. So we've got 91, and we're adding that to 1.8, which gives us 92.8. Difference therefore is 7.2. Write that down. Make that clear. You know, third isotope, whatever. I'll call it X is 100 minus 91 add 1.8 is 7.2, because that carries a mark on its own, the calculation, that's 7.2 there, which means we've got 1 out of 4 already. Okay, what would we normally do? Well, normally what we would do is we would say, right, to work out the relative atomic mass, we would do this number, the mass number, times its abundance, blah, 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 do that, add that to the next one, multiplied, add that to the next one, and that would give it our relative atomic mass. So we're going to do the same thing again. So we're going to say, and that would be over the total abundance, which in this case is 100. So we're going to do 32 times 91, and we're going to add that to 33 times 1.8, and we're going to add that to X times 7.2. Divide the whole, oh, that is the worst line ever. What is that even doing? Divide that by 100. I'll bracket these poorly, it would seem. And that's going to equal 32.16. And now it's a bit of sort of algebra. Let's chop it all around, work it all out. I'm not going to do it as each individual part here, but essentially what you're going to end up with is, through a bit of tomfoolery and a bit of magic, you're going to find out that X equals 34. Just like that. It actually comes out at 33.97, but you've got to round that, okay? You've got to put that to a whole number, because when we're looking at mass numbers, they are definitively integers, so it's got to be 34 there that you actually write down. Stick that down here, provided your working is all is all delightful. You will pull out 4 marks there. As far as I'm aware, though, you're not going to get 4 marks as the correct answer. You've got to show you're working, and obviously the individual stage between here and here, which I've not included, but really that's just a case of putting into a calculator and rearranging. You've got to include that. So, mass number 34, delightful. Describe how ions are formed in a time of flight TOF mass spectrometers. This is that new stuff now, which is the new way of doing mass spectrometry, which is ridiculous. Why they've changed it again, I have no idea, but there we go. So, quite easy though, it's not a lot here at all. Essentially, we apply a high voltage. And molecules or atoms, I guess whatever we're using, lose electrons. They've got molecules written down here, but it sounds ridiculous. I don't understand why they've put molecules when this question is looking at atoms. Anyway, molecules or atoms lose electrons. I would be honest, if this was me, I'd put atoms in this case because the question here is relating to atoms with the sulfur. It's not talking about molecules, so I would have gone atoms. But essentially, you apply the high voltage, and that causes the atoms to lose electrons, and that's it. That produces positive ions. Remember, positive, not negative ions. Another one, yeah. Explain why it's necessary to ionize molecules when measuring their mass in a time of flight mass spectrometer. Right. So, few stages here. Once we've ionized, we've got that sort of chamber. The next bit is those acceleration plates. You know, where we've kind of got these plates with sort of a hole in the center, where essentially the ions zip through here. Negatively charged plates, which fire into the ion drift stage, which is this part in the center. So, ions are accelerated, and then I'd make the point of atoms molecules are not. That'd be my thing. I'd perhaps actually say are accelerated by an electric field. Put that a bit of detail in there. It's not going to hurt. So that's going to be your first mark of the 2 here. Second one, and this is the important one as well, because obviously the ion drift isn't really important. There used to be, actually I'm not even going to bother going into what there used to be. It's the end of the ion drift stage there. We've had the detector in that ions create a current when they hit the detector, and then I would say again that to say atoms. Not sure why I've done it with what looks like 2 T's. Atom molecules would not. Again, 2 marks there, not too bad at all. Just need to know about how the mass spectrometer works really in those key stages. So next question. There's not even a total box anymore. They don't even total. Oh, this is appalling. Question 3. So there was a number of marks for that, but I don't know what it was about adding it up. It was something like 8 marks for that question. Question 3. Write an equation. The student states was the reaction with enthalpy change equal to the standard enthalpy of formation of CF4 gaseous. So, an equation, right, so essentially it's asking us just to write a reaction, right, yeah. You just write an equation to show the enthalpy of formation of CF4, but it's written weirdly. So, we're forming CF4, so how do we do that? Well, we add C, we add F2, that's its standard state, and we produce CF4. Balance that up. Remember, because it's enthalpy of formation, you would always keep this as 1 mole, which doesn't matter in this case. And we double those up. We do need to include state symbols, though, as it says, so don't get tripped out by that. That will cost you your mark. So carbon as a solid, fluorine as a gas, 2 of those molecules there equates to the 4 there, and CF4, carbon tetrafluoride, or tetrafluoromethane, probably what it would be called, as a gas as well. 1 mark. Explain why CF4 has a bond angle of 109.5 degrees. So we've gone from energetics to bonding. They're loving. I tell you what, the questions are muddled up like you wouldn't believe. Okay, how does this happen? Right, so think about the structure of the carbon tetrafluoride or the tetrafluoromethane. Essentially, we've got that. So why does it have a bond angle of 109.5? Well, first off, explain what happens, or describe it, I should say. It has 4 bonding pairs of electrons surround carbon. That'd be my first thing. 4 bonding pairs of electrons around carbon. The key thing there is that there's no lone pairs. We've got complete equal repulsion. Therefore, equal repulsion to basically spread them out as far as possible. And in the case of this tetrahedral shape, that equates to 109.5 to spread. As far apart as possible. So 4 bonding pairs there. The repulsion, the valence electron pair repulsion theory, tells us that actually they will be repelled into the furthest points possible, and that gives us this 109.5. There's 2 marks. That's a question. Table 2 gives some values of standard enthalpies of formation, and we're gonna have to work out an enthalpy change for this reaction here. So this is the reaction we've got, and we're told, oh, hold on. Oh, why are you doing this? So we're told the enthalpy change for this reaction is -2889. Right. Yeah, this is not a normal question. Right, they're really going for it on this, aren't they? So, horrible people. Okay, we're given formation values here. Obviously, fluorine equates to 0, but I'd probably include it anyway, just for a giggle. We've got CF4 and we've got HF there, also values as well. And these are the values to form these things. So we've already written an equation for the formation of CF4, but the formation of HF would be H2 plus F2 going to HF. Obviously, we've got to halve those, haven't we? Because if we don't have those, it's all going to go wrong. So I tend to always work in reactant cycles. You don't need to with these at all. You can do basically the sum of the products minus the sum of the reactants, but I don't do that. I do these as a cycle because I prefer the cycles. I think it's easy to work out what's going where, particularly in this one where you're going to have an unknown, which is this value here of formation for this guy here. Now we know to form this, ultimately, we know that we need to add carbon, particularly 2 carbons, and we need to add 3 hydrogens. Now we also have this change there, and we don't know this. This is our unknown. We know that this change here is 0, which is essentially F2 becoming F2. I'm going to include F2 in the bottom though, because actually F2 will become F2, but it has no enthalpy change associated with it. So we're also forming 2 CF4 there and 6 HF here. Now think of these as 3 parts. You've got this bit here, you've got this bit here, and you've got this bit here. Now let's put some values on here. So to form 1 mole, and actually before I do that, let's check the numbers are correct. We have here 2 C's, 2 C's, so that creates, and this is how a thermochemical cycle works. We have to have the same stuff on the bottom. This is this bottom box that people find more difficult. It is the linking part that allows us actually to have a whole cycle. So 2 C's form there, but 2 C's also would form up here. Obviously it's different times. We have in total 6 at 8 fluorine, which is 14, which is 7 F2, so that balances. And our hydrogens there, we have 6 with 3 H2, so that balances there. So key thing here is these enthalpy changes are for 1 mole, minus 680. This is going to be minus 680 times 2, and this one here is going to be minus 269 times 6. Got to be aware of that. Got to be aware of that. And this, obviously, this change here is minus 2889. Now we're trying to work out the change when we go from here to here. So I always say start here and finish here, but we can't go that way, so we go against it. So we go instead with these. So we're going to do minus 680 times 2, add minus 269 times 6. That's these accounted for. We're going against this arrow, so we're going to flip the sign. We went with these, so we're keeping them as it is. So we're going to add 2889 because we've gone against that, and that takes us to our finish point. So it's using Hess's law, this idea of the enthalpy change is independent of the route taken. So we start here. We haven't got to worry about F2, which is quite nice. So we go up here with minus 680 times 2, minus 269 times 6, up there against the minus 2889, and that will give us a value essentially for our unknown, which, according to this, comes out at minus 85. Now, I actually think there's actually quite a lot of work there for 3 marks, but if you're clued up with your Hess's law and your calculations, you'll be fine. Key thing here is that it's not a normal one. You're actually working out this change rather than what you would normally work out this one, looking at old past papers. So just bear that in mind. It is a little bit different. Question 3 still. Methane reacts violently with fluorine according to the following reactions. We're given an enthalpy change. And we're given some bond. Right, okay, so we're using... Right, so we've got to work out... Why are they doing this every time? Honestly, I feel like they're just making this needlessly hard every time. This is definitely harder than the past papers. So, rather than work out enthalpy change using the bond enthalpies, you're actually having to work out the enthalpy change or the bond enthalpy of the FF bond. The way I would always do this is I would say these bonds are broken, these bonds are made, therefore these are positive values and these are negative values, and we've got an enthalpy change. So, I'll just write that here so I can, when I scroll down, I haven't got to worry about not seeing it. Okay. I'll see if I can do it here actually. Go away. So what bonds have we got? Well, we've got methane. This is 4 marks, that's alright, we've got 4 minutes on this one. So we know with methane we've got 1, 2, 3, 4, and I tend to split it into, I'll do bonds broken here, bonds made over here, and then I'll put it all together at the end. So we've got 4 CH bonds to take into account. We've got 4 FF bonds. That's this whole side done. Over here, I've got the same thing here, but with Fs, so I've got 4 CF bonds, and I've got 4 HF bonds. So it's actually not too bad. The numbers here are reasonable. Put some numbers to that. So I've got 4 times 4, 1, 2, and I've got 4 times my unknown there, or X, probably is better than a question mark, but I'm going to use a question mark. I'm not a maths teacher, do that. 4 CF, so it's 4 times 484, and this one's going to be 4 times 562. And I'm just getting these numbers from this table here. Look, you should be able to work out which numbers are coming from where. Now, I would say these negative values because that makes the whole thing easier. You've just got to add it all together then. So, the final calculation bit would be 4 times 412, add 4 times x. I will put x this time. Add that to 4 times minus 484. Add that to 4 times minus 562. And that overall thing is going to equals minus 1904. Then, as with the other one, I'm not going to bother sort of doing all this stuff. I'm just going to basically go from here and just, you can work this all out yourself. You would end up with the FF bond, because maybe you've got to divide by 4. So 4FF equates, or 4x I should say, equates to 632. Divide that by 4, so 1 FF or X ends up being 158. So that's not the whole question though, because it is also saying here, a student suggested that one reason for the high reactivity of fluorine is a weak FF bond. Is the student correct? Justify your answer with a calculation using these data. Well, we can see, look at these bond enthalpies here, 412, 484, 562, and then 158. Yeah, student is correct. Student is correct. FF bond is much weaker than the I'd say the other bonds, because its value is lower or something like that. Would probably make more sense to do this the other way around, actually. Hold on. Lower bond enthalpy. What I probably would have said is, because it has a lower bond enthalpy, FF bond is much weaker. Would have been a better way of writing this, actually. Therefore, FF bond is much weaker than the other bonds. So the student is correct. But clearly, I mean, the most marks here are for the calculation. You're getting 3 for the calculation, you're getting 1 for this little bit of explanation at the bottom here. Next question. Again, no, not bothering to tell us how many marks we've got, but that's fine. Question 4. Colour solutions of X and Y react to form an orange solution of Z according to the following equation. Right, so X, Y, Z. Good. Student added a solution containing 0.5 moles of X to a solution containing 0.5 of Y with a mole. Right, okay. Good. Oh, I love these questions. Lovely list. It used to be A2, this used to be an A2 topic, this part of the equilibria. Has now been brought down into this year 1 or the AS portion of it. So, we know we start off with 0.5 and 0.5, and we know at equilibrium we have 0.2. Now I like to write this as sort of like a time 0 and as a time 1. So I would say at time 0 we have 0.5 and 0.5, and at time 1 we have 0.2. Now for me, time 0 is before reaction, where obviously we have 0 of Z. It hasn't been produced. Time 1 is at equilibrium, where we're told we have 0.2 of Z. Now, what we've got here is the reaction given, which is nice. And we've got to look at the ratio. The ratio here is 1 to 2 to 1. Now, initially what I would say is I'd look at the 1 to 1 thing because it's much easier. So the ratio of X to Z is 1 to 1. And I know that Z came from the reaction of X with 2Y. So if Z has been produced and is at 0.2 moles, that must have come from X because it's a 1 to 1, and Y as well. I'll do one at a time. So X is reacting. If we produce 0.2 moles of Z, we must have reacted 0.2 moles of X. So X must be 0.5 minus 0.2. So X is going to be 0.3. Not too bad. Now, Y is and Z have a ratio of 2 to 1, which means that whatever was produced of Z, half of that essentially came from Y, if that makes some sense at all. So although Z was produced at 0.2, we must therefore have had 2 to 1, no, I think I said half when I meant double. 2 to 1 is the ratio, making this more difficult than it is. If we've got 0.2 of that, that must have come from 0.4 of that. So 0.4 of this must have reacted to produce 0.2 of this, because the ratio is 2 to 1. If 0.4 is reacted, we know that we've got 0.5 minus 0.4 must be 0.1 there. So I'm going to assume ZX is fine. My explanation of Y was terrible. Do that once more. The ratio of Y to Z is 2 to 1. Because 0.2 moles of Z were produced, that must therefore equate to the ratio. Because it's double here, 1 to 2, we must have found that 0.4, which is just 0.2 times 2, 0.4 of Y had reacted. Because there was initially 0.5, we end up with 0.1 left. Oh, good. Draw a graph. Oh, I love that. Oh, why? I don't want this. On the grid below, draw a graph to show how the amount of Z changed from the time of initial mixing until 60 seconds had elapsed. It is just literally a graph. What a horrible thing to have to do. Okay, so you've got to use as much of the graph as possible. I would say 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, and 60 seconds. Time in seconds. You're getting 1 mark for all of the axes and scales and units correct. It's ridiculous. Amount of Z. Moles. We've got 1, 2, 3, 4, 5, 6 values of Z. zero point 0.2 split across here, so how am I going to do that? 0.51, 0.52. Yeah, you've just got to use over half of it basically. So 0.05, 0.1, 0.15, 0.2 would be how I would probably do that. Easy enough, isn't it? Yeah. Okay, what's going to happen? Well, go back up here, leave it here. After 30 seconds, there was no further change in colour. So after 30 seconds, we've basically got to have it flattening here. I'm flattening at 0.2 because that's what is produced at equilibrium, and I've started that flattening at 30 seconds because that is obviously the point there where we have no further colour change, so I know that it must have reached equilibrium at that point, although I am continuing through to 60 because it does ask for that. What we're going to have here, curve basically that joins these bits here, must start at the origin, that was terrible, goes from there basically, it's coming up and it's flattening out there, and that's your marks. 3 marks there, drawing a graph, brilliant, having a great time. I'll leave that up there for a second longer if you want to have a look at that, see what's being done there. No problem. Okay, 4.3, still continuing with question 4 and an equilibrium here. Linking it to Kc now, for this reaction. Oh, I've got to do equilibrium expressions and everything. Okay, so for this reaction, the equilibrium constant Kc is 2.9, moles to minus 2, dm6. Calculate the value for the concentration of Y at equilibrium. Okay, that's actually surprisingly straightforward. So first thing we have to do though is we have to work out our expression. So for this, Kc is always product over reactants. Well, Z was our only product. Square brackets, remember, because that's concentration. Our reactants, X, and remember it was 2Y. That's a Y, not an X. So it must be Y to the power of 2, or Y squared. So we know that actually that comes out at 2.9. So rearrange this. I'd probably rearrange this first actually. Yeah, we'll rearrange this first. We're trying to work out Y. Good. Y is the squared one. So we end up with Y squared is Z stays there where it is. Yeah, X multiplied by Kc. Then we can put some numbers in. So we know this is going to be 2. I would do this in a different way if I was you, but I'm just going to do this for sort of sake of time and ease and all the rest of it. 2.9 is our Kc value. We are given concentrations of X, means no conversions required. So X we can just put in as 0.4, Z we can put in as 0.35. I haven't got to worry about multiplying these up or anything, or squaring them or anything, or cubing them, because they're just as they are. 0.4 times 2.9 on the bottom, 0.35 on the top. Get our value, which comes out at, I don't know what the value comes out as, to be honest. I'm not working it out. But we must square that, remember. Square root, sorry. Okay, whatever this comes out as here, we square root that to finally come out with a value of 0.5493, which we're going to round appropriate number of significant figures, cheeky, 2, 2, 2. Therefore, it's going to be 0.55. Much more difficult compared to old papers here. They really are pushing for the understanding of significant figures and all the rest. That is a mark there. Well, not a mark, sorry. If you get this wrong, you do it to 1 significant figure or 3, you will lose that mark. So there's 1 mark based on the expression, 1 mark for the rearrangement, and then 1 mark for the calculation and answer to significant figures, giving us 3 in total. Not too bad. Obviously, I've skipped this stage of the calculation itself, but really that's just, it's some relatively simple maths at that point. Question 4.4. The student added a few drops of Y to the equilibrium mixture of X, Y, and Z in question 3. It shows how the colour of the mixture changed, give a reason for your answer. Right. Up we go, up we go, up we go. Back to here, back to here, back to here. So, we know that X and Y are colourless. Z is orange. At equilibrium, we have this nice balance here where we've got X and Y reacting to form Z, and Z breaking down to form X and Y, or X and 2Y. So, if we add some Y, what's going to happen? Well, this is Le Chatelier's principle, and it tells us that whatever change we make, the equilibrium will work to do the opposite. So, if we add Y, the equilibrium wants to remove Y. So, it will therefore react more X and Y together to reduce that to produce as more Z. In doing so, because it will increase the forward reaction, or it will better wording really is, it will shift the equilibrium position to the right, producing more Z, we'll find actually it will become more orange. So go down, blah 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 blah. Color change. More orange. More orangey, darkened they've got on here. Went more orange, I would just say more orangey. The reason, position of, really the mark scheme, if you get hold of the mark scheme for this, it's really easy to get off the AQA website. It's appalling. The answers are really shoddy. Whether this is just the specimen paper and they've realised they've made so many mistakes and the whole thing's going to be so much better, but I really think this is a poor paper, poorly written, and the mark scheme is really shoddy compared to the old ones. Anyway, since the equilibrium shifts to the right, Y to oppose the increase in concentration of Y. And that's going to give you 3 lovely marks. 1 for the top bit there, which is the colour change, 1 for the position of equilibrium shifting to the right, and 1 for the increase in the opposition. That's a key phrase to use whenever you have a question like this. You know, what happens when you increase temperature, blah, 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 to oppose the increase in temperature. Anything like that, you've got to put that opposition part in. Student warmed, oh here we go, look at this. The student warmed the equilibrium mixture from question 4.3. Predict the colour change, if any, when the equilibrium mixture was warmed. So, back up we go to the equilibrium. We're given an enthalpy change. It's an exothermic reaction in the forward direction. So if we increase temperature, it wants to decrease that, and it must do so by shifting or favouring the endothermic reaction. So in this case, it will shift to the left because that's the endothermic way. It will favour that backward reaction, producing more of colourless X and colourless Y. Therefore, the colour would fade. No explanation required there. The colour would fade. But I've given you a little bit of an explanation as to what's going on there. So yeah, question 5, here we go, new one. This question is about the chemical properties of chlorine, sodium chloride, and sodium bromide. Sodium bromide reacts with concentrated sulfuric acid in a different way from sodium chloride. Write an equation of this reaction of sodium bromide. Explain why bromide ions react differently from chloride ions. So, the reaction of sodium bromide with concentrated sulfuric. Okay, so we are doing that one. So sodium bromide. So NaBr, and we're reacting with oh, hiccups. That is not ideal, is it really, when you're making a video? There we go. H2SO4. So we're going to produce some sodium sulfate, Na2SO4. We're going to produce some bromine, Br2. We're going to produce sulfur dioxide, and we're going to produce water. And of course, we're going to balance this up so that it all works. 2 there. Nice, that's equal there. What do we got? I've got 2 S's, so we're going to have to double this one up. Double that one up. 2, 4, 8, 8. Yes, balanced. Good. Right, explanation. Why does it react differently? Why do the bromide ions essentially react differently from the chloride ions? Well, what do we know about bromide ions compared to chloride ions? Bromide ions are bigger. Must be comparative. Bigger than chloride ions. If they're bigger, more easy to, basically more easy to lose an electron. So bromide ions are bigger. Lose electrons or are oxidized more easily. So bromide ions are bigger, and therefore they lose electrons more. That it does say more there. That is a more. Lose electrons more easily, which is great. And obviously these bromide ions are the ones in here. We've got this Na plus and the Br minus there. So the bromide ions are lost more easily to become, in this case, the bromine, because they are bigger. Okay, 3 marks there. 5.2. A colourless solution contains a mixture of sodium chloride and sodium bromide. Oh, look at this. 6 marker. Nice. So, 6-mark question. These are important. It's important first off to make sure your answer covers all the points. Excuse me. And it's really important to make sure that you write in a very logical, nice, clear way. If you write it just absolutely, just pathetically poorly, you aren't going to get the upper marks, because the way it's marked, it's true at GCSE in the same concept, it's marked as levels. So here basically I'll read you the levels. So level 0, insufficient correct chemistry to warrant a mark. Basically you suck, so you're not going to get any marks. Level 1, that's 1 or 2 marks only. You can't get anything higher if you've decided that you're level 1. 2 stages are covered, but the explanation of each stage may be incomplete or may contain inaccuracies, blah 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 blah. Contains some isolated statements, these are not presented in logical order or show confused reasoning. Going up to level 2, we've got all stages covered, but the explanations may not be correct to make inaccuracies, or they're not brilliant. Or 2 stages are done very, very well. Then generally it's coherent, but it's not very logical still. Level 3 is where we're looking for everything being completely logical, all explanations being absolutely correct, and all of that nice stuff there. So, we've got 3 stages basically that we've got to account for here, because what we're doing is we're using silver nitrate and any of the reagents to prepare a pure sample of silver bromide from the mixture of sodium chloride and sodium bromide. So, really, it's. I like this question actually. When I first saw it, I kind of went, "Oh no, this is terrible. I don't know what to do." But actually, when you think about it, it's a clever way of asking what you should know anyway, and that's basically it's flipping on its head the test for the halides. So normally, to test for halides, you would add silver nitrate, and you'd add a bit of nitric acid as well. But you'd add silver nitrate to the sample. So that's what I would say. First bit, add. So now you've got to do this as prose, but because just for the sake of time and all the rest, I'm not going to. But you have to write this. I believe you've got to. I think you've got to write this. You know what? You might not have to actually write this as prose. I think you might be able to write this as bullet points. Look at the mark scheme. That's how it's written in there. But then it's a mark scheme. I think you actually can write this as bullet points, which is great, which I'm going to do anyway, but I would actually recommend you do it in this case. It's not mentioning about the standard of your written quality of communication or whatever, so I don't know, dodgy one there. Not sure. Probably go for prose if you're unsure, but I'm going to use bullet points because I am. So add silver nitrate to the NaCl and NaBr mixture. Now what we'll find is that in doing so we will produce, we are asked to do equations as well, that will produce precipitates of AgCl and AgBr, and then we can do equations to show those. So essentially we've got I would probably they've got them here as full equations. I'll do them as full equations, but I think you'd be fine actually doing them as ionic equations as well. And then the other one's just going to be NaBr, AgBr. Everything else remains equal. So what we've done now is we've still got a mixture, so it's still pretty rubbish. We've now got, though, silver chloride and silver bromide mixed together. Well, how can we separate those? And they're classing this as stage 1, production of the precipitates, basically. Next bit is how can we basically get silver bromide from this mixture of silver chloride and silver bromide? What we can do is we can add dilute ammonia. And what we'll find is that will cause the silver chloride to dissolve. Okay, and so say that Ag, and we'll probably do this in excess. We'd add loads of it to make sure we dissolve all of it. Silver chloride dissolves because we don't want to end up with some silver chloride left over. We want to make sure that's all dissolved. So we add excess of that. Silver chloride will dissolve. And what we'll find then is, obviously, we're left with the silver bromide on its own. Equations here for what's going on. We've got our silver chloride reacting with our ammonia to produce this wonderful silver complex and chloride ions there. Obviously the silver bromide is not reactant, so you haven't got to worry about that. We need to balance this though. It's going to be balanced like that. Okay, that is stage 2. We have now essentially isolated the silver bromide. It's now in solution, but that doesn't help because we are asked to produce a pure sample of silver bromide. So what are we going to do? Okay, filter to remove silver bromide. That's good, but it's not pure. We've got to therefore wash it. So wash silver bromide. That should in theory now purify a little bit. Well, it's not really going to purify, it's just going to clean it up and then dry it. I don't think it does ask for a dry sample, but it's not a bad thing anyway to dry it. So this is our stage 3. Those are essentially the points that you've got to make. Now I don't know exactly how they actually would mark this. I don't know. I mean, you've got to include, because the problem is if you get hold of the mark scheme and look at it, you'll see here I've made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. And I've covered stage 1, 2 and 3. So I'm fine. I've got all the points here. And this is just taken from the mark scheme basically, but reworded into what I would say if I was doing this exam. But the problem is, I don't know which of these bits you'd have to include. We'd have to include all 10 points to get 6 marks. I don't know. I mean, certainly it is asking for you to have equations, so you've got to include equations where appropriate. If you're not sure of them, don't put them in, would be my advice. But certainly excluding the equations, you should have no problem actually getting the wording of this there. But it's about looking at this and realising that it is taking stuff you've already learned, but flipping it on its head slightly. And actually, it's quite a nice question. 6 marks. There we go. Anyway, that's done. A bit more space there. Okay, question 5.3. Write an ionic equation for the reaction between chlorine and coal to dilute sodium hydroxide solution. Okay, standard one that really just needs to sort of learn. Ionic equation. And actually, the mark scheme is wrong on here. To make it clear, the mark scheme does not have the minus symbol on the H, on the OH there, and actually calls it HO, which I find very strange. But anyway, producing that chlorate, 1 chloride ions and water. Obviously normally we would have to, yes, balanced. Normally you would probably write it as NaOH, but do bear in mind it is asking for an ionic equation, so don't get tripped up by that. And then give the oxidation state of chlorine in each of the chlorine containing ions formed. So it's going to be -1 and it's going to be +1 there. Easy. Next question. Question 6. More calcium. We've already talked about calcium once. They're loving calcium today, aren't they? Maybe they've got sponsored by calcium. Anyway. Question. Oh, 8 marks. There's a question. It's 8 marks. Oh, I don't want this. Anyway. This question is about the reaction of calcium compounds. A pure solid is thought to be calcium hydroxide. The solid can be identified from its relative formula mass. Relative formula mass can be determined experimentally by reacting a measured mass of the pure solid with an excess of hydrochloric acid. The equation of this reaction is as follows. Blah, blah, blah. The relative acid can then be determined by titration with the standard sodium hydroxide solution. You are provided with 50% meters cubed 0.2 mole per decimeter cubed hydrochloric acid. I'd like Good. Yep. Love this question. So what is essentially going to happen here? There's a lot more in this question than there initially appears. This is basically the question itself. You are provided with this amount of hydrochloric acid and then outline, give brief practical details, how you can an accurate experiment to calculate the relative formula mass of the solid using this method. Right. So this is the amount of hydrochloric acid you've got. Now, it says you should use an excess of hydrochloric acid, but you need to actually make that really clear in your method, which I think is a bizarre mark. Even when they give that, you actually get a mark for saying use the acid in excess. A measured mass. Well, you've got to calculate that measured mass. So first thing to do is I mean, on the mark scheme, it says statement that there must be an excess of acid. So acid must be in excess. And now you've got to basically make sure, if you were doing this for real, you would have to make sure that the acid is in excess. Therefore, you'd have to make sure that the solid you put in contains less moles than you would get in the reaction if that makes any sense. So the moles of acid must be greater than the moles of calcium hydroxide present. So you need to work out though first off, how many moles of acid do I have? Now moles is concentration times volume, so 0.2 times 50 over 1000, and that comes out at 1 times 10 to the minus 2, or 0.01 I think, isn't it? 0.0112. Yeah, 0.01, whatever you want to call it, 10 to the minus 2, whatever. Now, if you know the ratio is 1 to 2 in terms of the reaction there, if I've got that many moles of acid, if I add this whole lot in, moles of calcium hydroxide maximum is basically going to be 1 times 10 to the minus 2 divided by 2, which is obviously going to be 5 times 10 to the minus 3. When I say maximum here, really what you've got to make sure is that your moles of calcium hydroxide are less than this. I'll keep it as max. That's the maximum really, but it should be less than that. So we've got to work out the mass therefore of the solid as well. So that would equate to this value here, then we obviously need to have less than that. So mass is going to be worked out as this value of moles times 74.1 is what you get from the periodic table. So and that comes out to be 0.371 grams. And I think at this point it's worth saying mass must be less than 0.371 grams. That is key. By having a mass less than 0.371, so say you picked 0.2 for example, you probably wouldn't want to go for 0.370, say you pick 0.2 or 0.1, you are therefore ensuring that you have more moles of acid, therefore the acid is definitely in excess. So this is kind of some of the preliminary work you would have to do if you were going to carry this out. But the actual practical itself, what do you actually do? So we've got to basically got to start again right from the beginning. We've actually got to say, right, so this is the calculation aspect of what we're going to actually do. So measure 50 centimeters cubed of acid. Now it doesn't matter really how you do this. They're saying use using a pipette. I would probably actually use a burette personally. You could use a pipette, I suppose, but a burette's going to max it up. Pipette, if you've got a 50 centimeter cube pipette, then really you've got to give a way of measuring it. Probably steer away from measuring cylinders though, only because we are trying to be accurate, and therefore we want to use equipment which has got, you know, sort of a high degree of accuracy. Measuring cylinders have less so. Measure that out. Into a conical flask, because we are going to titrate, and add weighed solid. Okay, what we're going to do, it's a really, this mark scheme, get hold of the mark scheme, have a look at it, it's just bizarre. So we've got our conical flask ready now. Obviously we're now going to titrate into that. So add, wow, actually not given, oh, a standard sodium hydroxide solution. You've got to actually give, there's no concentration given, so probably you use equimolar there. Titrate using 0.2 mole per decimeter cubed NaOH. And then, of course, what we would do is we would record volume once indicator changes colour. Actually, what we'd probably do here is, I think we should add indicator up here. Mark scheme doesn't really say that, it just suddenly mentions indicator down here, whereas actually, for experimentally, we're going to add it up here, aren't we? We're going to add it before we start titrating. So I'd add indicator there. Doesn't require you to name an indicator. I would always be careful with naming indicators, because often then you would be required to give the actual colour change, which is a little bit of a dodgy one. What I would say is don't name the indicator if you can help it, and then just talk about the colour, unless you know for definite phenolphthalein changes colour in, you know, alkali and acid and the colours that it has in each. I always forget, basically, so I tend to not try and write that because I don't want to forget and get it wrong. So record the volume once the indicator changes colour, but we have to have added that indicator in. I think that's a mark scheme. Sloppy again on the mark scheme there. They should have me checking these mark schemes. I'd be all over it. Finally, because ultimately we're trying to identify it using its relative formula mass, we need to actually calculate its relative formula mass at the end. So what we would find here, I tell you, it's a horrible question. What you're going to find is that when you add the calcium hydroxide to the acid, because it's an excess of acid, the calcium hydroxide is going to react with a portion of the acid, which is going to leave some acid left over. So some acid is going to remain afterwards. And when we're titrating with that unreacted, against that unreacted acid. So the volume that we've got here is going to be the volume of the sodium hydroxide that has reacted with that amount of acid that we are unsure of. So knowing, as we would, because we know the volume now of sodium hydroxide and we know the concentration, we could work out the moles of sodium hydroxide. So we could calculate the moles of sodium hydroxide, and this would be equal, this is how I would do it. This would, and I actually think the mark scheme is actually wrong, but I'll do it my way because I think it's better. This would be equal to the moles of HCl that were unreacted in the conical flask, as in at the beginning, once you've added the calcium hydroxide, the number of moles of hydrochloric acid there would be equal to the number of moles of sodium hydroxide that we use. And the reason I know that is because, go away, sodium hydroxide and HCl react as a 1-to-1 reaction to produce NaCl and water. So it's a 1-to-1 reaction there. So I know that whatever moles of sodium hydroxide I have, let's go away, it must be equal to the moles of hydrochloric acid that remained after the initial reaction with the calcium hydroxide. So this question is long. Once I have those moles of hydrochloric acid afterwards, I know how many I initially had, so we can work out moles of hydrochloric acid that initially reacted, and I think I'd probably give an indication of what's going on there. So I would say that would be equal to the excess, which in this case, remember, was 5 times 10 to the minus 3, minus this value here. I would probably say moles from titration, but what I would do is I'd explain here how you do this. Calculate moles of sodium hydroxide. I would say vol of NaOH divided by, and that must be 0.200, which is our moles of sodium hydroxide we're using, times the volume of sodium hydroxide, which obviously we don't know, but we need to divide that by 1,000. And that's what I would do there. I would just say how that works, and then I would say, yeah, that would in your explanation here, that therefore equates the moles from titration, which is going to be there. That's how moles reacted. Finally, that gives us the moles, therefore, of the hydrochloric acid that actually reacted, and we'll call that X. Then what we can do is we can say MR, so it's going to be mass over moles. It's going to be X divided by 2, I believe. Yeah. Now the mark scheme doesn't do this, and I'm a little bit unsure why it doesn't do this, to be honest. When you work out the moles of hydrochloric acid that actually did react, so you've got your excess, you've got the leftover stuff. When you work, the difference between those is the moles that actually reacted with the calcium hydroxide. When you've got that, because of the ratio, you've actually got to halve that to find the moles of calcium hydroxide, therefore, that reacted with the initial sample. Mass divided by that number of moles should give us an MR, which we can therefore check. Now, there's a lot of work there. A lot of work. I think that's one of the most in-depth questions I think I've ever come across in my time of teaching. Really, you just got to do your best on that kind of question. I think it's going to be, whether something like this comes up on the real thing, it's very vague. There's a lot of information required from you there. But I will move on. I'll just go through this so you can actually see all the parts that I've written. If you've got any questions about that, do by all means ask. Right, so still on question 6. Love this. And we continue now. Question 6.2. A 3.56 gram sample of calcium chloride was dissolved in water and reacted with an excess of sulfuric acid formed precipitate calcium sulfate. Percentage yield, blah, 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 blah. Calculate the mass of calcium sulfate formed. Give you an answer to promote a number of significant figures. So, initially, let's work out our moles of calcium chloride. Got our mass. I know that our thing is MR is going to be that 3.204 times 10 to the minus 2. So, blow my mind these questions today. So, I've got moles of calcium chloride. Okay, so we can work out the moles, therefore, of calcium. Right, okay, yeah. Is also going to equal to 3.204 times 10 to the minus 2. The reaction here is a one-to-one reaction, which really you just kind of got to know that, got to work out for yourself. One-to-one reaction. So the moles of calcium sulfate produced are 3.204 times 10 to the minus 2. Now that's assuming for 100% yield, but it's not. Percentage yield is 83.4. Therefore, we have to account for that, and so we would multiply that by 83.4 divided by 100. Or you could do it by 0.834, whatever you want to work it out. That's going to give us a number of moles of 2.672 times 10 to the minus 2. And then our final bit here is calculating that back up to a mass. So mass of the CaSO4 is going to be, mass is moles. Yeah, 2.672 times 10 to the minus 2 times MR 136.2, and that gives us a final answer of 3.64. Again, significant number of significant figures here. 3, so it's got to be to 3.64 there. Next question. Oh, it just keeps coming. Oh, this isn't too bad. So it's, straight away I'm looking at this. We've got a PV nRT situation there. PV equals nRT. We start off with that though. Example of pure magnesium nitrate. And what's decomposed by heating is shown in the equation. The 3.74 gram. Okay, so we know our pressure. We don't know the volume. That's our calculating one. We know R and we know T. We've got to work out the moles first. So 3.74 times 10 to the minus 2 gram sample of this was completely decomposed by heating. So we'll work out how many moles we have of this first. So moles of MgNO3 2 is going to equal 3.74 times 10 to the minus 2 divided by the MR, which is 148.3. That's going to give us 2.522. You obviously have to work that out yourself. It's not given. Times 10 to the minus 4. That's our moles. That's a good thing. That's actually going to get you one delightful mark. Now, moles of gas. Ratio of this magnesium nitrate to gas is 2 to 5. Therefore, if we do moles of gas, which is important because we need that for here, if we do 2.522 times 10 to the minus 4, this is how I would do it. I would say divide by 2 times by 5, and that's going to give us 6.305 times 10 to the minus 4. That's our moles of gas overall. We're not distinguishing between the nitrogen dioxide and the oxygen. We're just basically talking about the entire gas, because that's what's going to be used for this ideal gas equation. So we've got our moles now, so we can finally put this in. So V is equal to nRT over P. 6.305 times 10 to the minus 4. R is always 8.31. T is 60, add 273. Remember, it needs to be in Kelvin. It's given us 6 degrees Celsius. P is 100,000. And actually, that's all you need to do. Okay, so that gives us our volume. Now bear in mind that's going to give us a volume of 1.745 times 10 to the minus 5 meters cubed. They ask for it in centimeters cubed. You've got to times that by 1,000,000 to get the actual value, which comes out 17.5. Appropriate number of significant figures. All our values are given to 3 significant figures, so 17.5 is fine. So I've rounded that and then put it obviously into my correct portion, my units there. The mass of magnesium oxide obtained in this experiment is slightly less than expected from the mass of magnesium nitrate used. Just one practical reason for this. Any basically idea where you're going to somehow lose. So solid lost in weighing is a good one. The mark scheme says some solid blown away with the gas produced. Anything the idea of solid being lost, but don't just say solid lost, say where the solid is lost from. That thankfully is the end of the sort of written portion now. I'm on to section B, which is this new delightful thing here where you've got a multiple choice, fill in the gaps. Do please bear in mind the instructions here, it's quite important. If you want to give an answer, you must colour this in as so, not giving ticks, okay? Follow the instructions. This has all been marked by a computer, so don't get it wrong. So which of these atoms has the largest atomic radius? 4 choices: argon, chlorine, magnesium, or sodium. Basically what we're going to do, if we've got our periodic table like this, now furthest left are our bigger atoms here, and the higher up, the lower down we are in a... Actually, no, they're all in the same group, aren't they? No, they're all in the same group, that's fine. So it's going to be sodium for this one, because our furthest left, it's as we move across the periodic table, across the period, the increased number of protons actually constricts and pulls in the atom and makes it smaller. So the biggest one is going to be this far left here. It's going to be sodium. Which of these species is the best reducing agent? So a reducing agent is something that oxidizes. No, it's not. Oh my god. A reducing agent is something that reduces amazingly, but in itself it is oxidized. Now oxidation is loss of electrons. So basically what it's asking is which of these species is the best at losing electrons. So we're looking for either this or this, because they're our negatively charged ions, so they're the ones that are probably going to look to lose electrons more than the diatomic molecules here. And really the one that's biggest is going to be the one that loses electrons most easily, so iodide ions are the one. Moving down, which of these pieces of apparatus has the lowest percentage error in the measurement shown? Right, basically here you're looking for which one's the lowest percentage error. So the percentage error is worked out by doing, in here you would do 0.1 over 25, here you would do 0.5 over 25. So already I know that this one is going to be smaller than this one, so it's not going to be that one. Here we're going to do 0.1 over 23.2, so I know that 0.1 over 25 is actually going to give us a smaller number, so it's not going to be this one either. 0.001 over 0.150. Well, let's factor that up slightly. That would be the equivalent, and you can actually do this in your head without a calculator. That would be the equivalent of 0.1 over 15, I believe, which means this one is going to be our greatest one. I would have done it on a calculator, but I haven't got a calculator on me. So A is going to be our lowest percentage error there. It's basically the error itself of the equipment divided by the measurement. 11. The student is provided with a 5 centimeter cube sample of 1 times 10 to the minus 2 multiplied cube particle class. The student is asked to provide method per particle. Right, what I would do, I'd work out the moles here. So moles concentration times volume, 1 times 10 to the minus 2. I will use a calculator for this actually. So our answer here is 0.1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, or 5 times 10 to the minus 5. Okay. The reason I've done that is because that is the number of moles that are being added. Okay. And basically what we want to do is we want to look to turn that into this concentration here. So if I know most of my number of moles that's gonna be in the overall sample ultimately, I can then work this through and I can say, well, if concentration is moles over volume, therefore volume is moles over concentration. I can work out the volume that this final solution must have in order to have this concentration, bearing in mind the number of moles that are in it. So if I've got 0.00005 moles, but the concentration I'm going to get is 5 times 10 to the minus 4, which is the 0.0005, then I know that the overall volume must be 100 centimeters cubed, or it comes out 0.1 decimeters cubed, 100 centimeters cubed. So it's saying how much water should be added to this initial sample. Well, the answer is going to be, because I'm trying to get to 100 centimeters cubed in total, I've got to add 95 centimeters cubed, because I already have initially 5 centimeters cubed in my sample. Okay, so I add 95 centimeters cubed, gives me a total volume of 100 centimeters cubed. There's perhaps an easier way of doing that. That's the way I would do it. And that's going to get us to our lovely little point there. Which of these species has a trigonal planar structure? So 12. Really, all you've got to do here is you've got to go through and you have to calculate each one of these using the method, looking at the individual atom, the central atom, looking at what's coming in, accounting for each one of those, adding in the right numbers. Then you've got to account for any ions. Finally, divide that by 2 to find out how many pairs you've got. You end up finding that actually it's this one here, BCl3. And I'm not going through that one too much, so I want to keep very conscious of the time of this. We've only got a few more of these to do. I think, honestly, I've got quite a few of these to do. Blah. Okay, which of these comments is the highest boiling point? So straight away, intermolecular forces, we're thinking about hydrogen bonding. So this one's going to have hydrogen bonding. These are not going to have hydrogen bonding. Therefore, I would say it's going to be A. That is going to have the highest one here. These are just going to have the permanent dipoles, but of course, intermolecular, the hydrogen bonding is stronger. 14, which type of bond is formed between nitrogen and bromine when a molecule of ammonia reacts with a molecule of BF3? Yeah, the idea of these molecules reacting, generally speaking, we're looking for that coordinate bond in there. And if you look at the idea of the nitrogen here, has that lone pair of electrons, and ultimately it will bond with the boron there, creating this new compound. So a coordinate bond, or data for covalent is another way to call it. Which of these has the highest electronegativity? We're looking really for the highest electronegativity. We're looking for the atoms that are smallest, but with the highest number of protons, really. So far right hand side of the periodic table, and we're going to get chlorine there. Chlorine's going to be our one that we're going for. Yeah, small enough, plenty of electrons, nice. Not going to be argon, remember, because argon doesn't actually react, so it can't have any electronegativity. Which of these atoms has the smallest number of neutrons? Okay, nice, reasonably simple one here. It's going to come out to be lithium there. It's just a case of going through and working those out. I'm not going to spend time on that. 17. Which of these substances does not show hydrogen bonding? Well, this one does. This one does. Right, it's going to be this one, because in this case, hydrogen is not bonded directly to the fluorine. Hydrogen is bonded separately. It's bonded to a carbon, therefore it's going to be this one that does not show it there. What is the formula of calcium nitrate 5? 5, right, so really the way this question's going is it's saying the nitrate 5, the 5 there is equating to the nitrogen of the nitrate group. So when I look at this here and look at my NO3, this is going to be plus 5 there, which means that overall this portion here, NO3, is going to have a minus 1 charge. Therefore, with the calcium having a 2 plus charge, it must be CaNO3 2. 18. Yep, 19 down. What we're looking at here, which of these elements has the highest second ionization energy? Bizarre question. So which of these has the highest second ionization energy? Right, it's got to be sodium. In sodium, after that first electron is taken, we drop down into that next shell. Big jump there, massive. Magnesium is still in the same one. Neon is the same one again. Argon's the same again. So it's got to be sodium, because after that first electron, we drop down into the next energy level, much higher. 20. Which of the following shows chlorine in its correct oxidation states in the compound? Right. So here we know it's minus 1. Here it's going to be what? Minus 6 plus 1. So I would say it's got to be that one. I'm just using my laws of redox really to work that out. Obviously 8 hydrogens plus 1, your oxygen's minus 2, plus 1 for the group 1 metal, minus 2 plus 1, work out all the differences there, not too bad. Which substance is not produced in a redox reaction when solid sodium iodide reacts with concentrated sulfuric acid? So question 21. It's this one here. And that, again, it's just understanding of the halogens really to go through and make sure you know that. 22, last one. Which of the following contains the most chloride ions? Wow. Right, so we've got to work out really how many moles we've got of each of these. So once you work those through, it comes out at this one. The reason it's saying this, basically the way it's working is that when we dissolve something, we're going to find that these chloride ions actually become free. Once dissolution has taken place, the chloride ions become free. So we're looking for although initially this one may seem like it's going to be the highest because we have 3 chloride ions, there's not as many moles initially of the aluminium chloride there. So with this one we have enough moles of aluminium chloride that when it then breaks down each calcium chloride giving us 2 chloride ions, we have the highest number of chloride ions in that one. That is the end of that. It's been quite long. I don't know how long I've been sat here. Again, hopefully it's of some help. Do get hold of me if there's any problems, but good luck with that one. And yeah, there you go.